Hello and good morning. My name is Les Hurdis of Agri-EPI Centre, and I'm pleased to start the webinar today on emerging ultrafine bubble technology. I'm going to be joined by four esteemed colleagues, Dr. Anthony Finesse, Dr. Steve Ward-Smith, Alex Giles, and Dr. Richard Glass. And each one I'll be introducing prior to their sessions. The aim is this morning is that we look at what are nanobubbles, what's their national significance, their remarkable properties, and the economic and environmental significance of ultrabubbles going into the future. To start the show, we're going to hand over to Dr. Anthony Finesse, who's Honorary Professor in Engineering at Harper Adams University. He's also Chief Scientific Officer of Magrow Tec, and with over 50 years' experience in research consultancy. He's recently finished an Innovate-funded feasibility study into ultrafine bubbles, in which Agri-EPI Centre and CHAP were partners. So without further ado, let me hand over to Dr. Anthony.
Okay, good morning, everyone. Thank you, Les, for that introduction. Over the years that I've been involved with research and technology, it has become abundantly clear to me that things are invariably more complicated than they first appear. And that's certainly the case that we have with nanobubble technology, partly because of the multifactorial issues that relate to that technology. Next slide, please. Now, and the next slide, please. There we are. As I said, things are invariably more complicated than they first appear. That doesn't mean to say that this presentation is going to look at the technicalities so much of the nanobubble technology, more to do with looking at the features which will distinguish it as a disruptive technology. That's technology which has relevance in different sectors of industry and commerce, but also can have radical influence upon processes, for example, tens of % improvement in processes and so forth. Now, this is becoming particularly important, this type of technology, when we're faced with so many challenges that we have just now, global challenges. Next slide, please. We've all been faced with the pandemic, of course, but we also have the energy crisis, we have climate change, and the associated issues to do with the associated planetary boundaries, and so much more. And we're faced also with the issues, the global issues to do with food security. And this is particularly important, of course, for the farming community, where they've not only got to, next slide please, deal with the rising population and growth and how that relates to food needs, but also to provide solutions which are environmentally friendly as well. So a double challenge, and more than a double challenge for farmers, of course. There are a number of technologies, of course, which provide the armory within precision farming per se to address these challenges, including the Internet of Things, data management technologies, remote sensing technologies, and so forth. So any technology which offers the opportunity to solve these problems in an environmental way is to be accepted. Occasionally, a technology comes along and it offers those features which offer a great deal of potential in regard to solving these global problems. I believe nanobubble technology is one of those, but it's a technology that's very much at its emergent stage. Next slide, please. Also, it's important, I think, in dealing with technologies, particularly emergent technologies, that one looks at how they can combine with other technologies in order to facilitate solutions. Within Magrow, the company for which I am the CSO, we have interest in magnetic assist technology as a sustaining technology, a retrofit technology, which forms the basis for most of the revenue generation for that company. But also it has those benefits which relate significantly to the issues of these global challenges. The technology of magnetic assist technology has demonstrated a lot of benefits with regard to spray deposition, reduction in drift, but also reduction in the need for inputs, water inputs, nutrient inputs, pesticide inputs, and so forth, all resulting in reduction of costs. So very important indeed in that respect. And the company also sees that complementary technologies, like the technology we're now dealing with, and we're referring it to as bulk nanobubble technology, that's technology of bubbles within the bulk medium. And we're seeing that as an important emerging technology because of the properties that these bubbles exhibit. Next slide, please. And it's because of the research and market review of publications and so forth that's revealed a rich and potentially revolutionary foundation for interactive research, knowledge generation, and applications, particularly with regard to these bulk nanobubbles. Next slide, please. But the technology itself as a legacy in microbubbles, these have been used over the last few decades in very significant ways in other industries like the mineral industry and in cleansing industry, water treatment, and so forth. And it's these properties of the bulk bubbles that provide the basis for the nanobubble technology, which stems from this legacy of microbubbles. A legacy that translates into enhanced potential as a result of these bubbles. Existing applications already found to exist in such diverse areas as, next slide please, water treatment and pollutant removal, surface cleansing, mineral flotation of fine and ultrafine particles, carriers for fragrances and flavorings, bioremediation, groundwater, and medical applications, and the list goes on. Next slide. Industrial wastewater treatment, sterilization, tissue preservation, disease and pest control, acceleration of metabolic functions in plants, and so forth. So you can see already this legacy relating to microbubbles also has the similar potential, but greater potential with respect to nanobubbles, partly because they are more stable and they last longer than the bubbles, the microbubbles that form the basis of these legacy applications. Next slide, please. What is important in all this, though, is translating the knowledge that we gain from understanding the scientific basis for these technologies into the commercial objectivity. That's extremely important. We get from the science sector the foundational knowledge, but we need to view that in the practical sense. How can it be scaled? How can it be applied in more practical settings, particularly with regard to media properties, as we shall see. Next slide, please. So what are nanobubbles? Well, there is a standard, an ISO standard, which defines them as bubbles being less than 1 micron in diameter. And typically we're looking at bubbles between 10 nanometers and up to 1,000 nanometers in diameter, quite often in the region of 100, 200 or so nanometers in diameter. Next slide, please. So we're dealing actually with bubbles that we cannot see. They're invisible to the naked eye. We're probably more familiar with the bubbles that we see in champagne glasses, where they rise to the surface and disperse. Nanobubbles don't. They don't have that buoyancy. They don't rise to the surface. They're more stable, and they exist longer in the medium that we're dealing. In this case, we're dealing with aqueous medium. They're about the size of a virus, the COVID virus, for example, and can parallel also in the size of bacteria. Although we can't see them, we can reveal them if we use a laser source, a green or a blue laser source. And this exploits a property known as tidal scattering. This is a property that one associates with colloidal solution or colloidal dispersals. Next slide, please. So what are the key properties then that distinguish this technology as being a disruptive technology? Well, the surprising stable gas-liquid interface that they have. I mentioned that already, and we'll say a bit more about the stability as we continue through this presentation. They also have this surface area to volume characteristics which can be exploited. With large populations of this bubble, we can actually have quite a significant surface area available for delivering what is on the surface of those bubbles, including the charge associated with what is on the surface of those bubbles. They have this internal and surface adhesion carrier characteristics. They can carry gases within the bubble and adherents attached to the surface of the bubbles. They have influence too upon the aqueous medium cell and can affect their surface tension, density, viscosity, and so forth. They have this surprising longevity, which is linked in with the neutral buoyancy and the stability of the bubble. And the list goes on. Next slide, please. So we also have these colloidal properties that we can exploit. That's to do with the way in which they can perhaps aggregate within a medium or not, as the case may be. We can exploit those colloidal properties in different ways. There is a size and penetrative capabilities. Because they're so small, they've got the capability of penetrating into leaf surfaces, for example, or root structures. There are also the physical and chemical properties, which include factors that influence the population size and the properties of those bubbles, include temperature, pressure, pH, gas concentration. And these cosmotropic and chaotropic, these are properties that relate to the organizational capability of the ionic entities. And added to that is valence and surfactants. And we'll say more about those in the presentation. And the slides that follow really are there to provide additional information rather than as a vehicle for this presentation. So I will skip through those slides fairly rapidly. Also, the bubbles have this capability that they can form nanoshells and particles, and these can have particular advantage in the medical sector, for example, as we shall see. Next slide, please. So, just go through the properties very rapidly. Bubble size and population I mentioned. One can exploit that surface area in various ways, as we shall see. Next slide, please. So, they can generate in various ways. The range of production methods, which include mechanical shear, pressure reduction, Venturi, for example, ultrasonic cavitation, electrolysis, electrostatic effect, solution substitution, each invariably a consequence of either homogeneous or heterogeneous nucleation. Next slide, please. As far as the actual systems are concerned for generating bubbles, there's more to the eye than just the actual generator mechanism itself, or the generator components within the system. Ideally, one is looking at system components which facilitate control of the nanobubble population. That's becoming increasingly important based upon what we've found from the investigative study of the Innovate funded project. One aspect which is particularly relevant in that respect is being able to monitor the nanobubble population. Characteristically, one is using pretty sophisticated equipment, costly equipment, to measure the size and distribution of these bubbles. Ideally, we'd like a lower cost facility that allows us to estimate population sizes and control them accordingly. But as you can see in this schematic here, there are various components to do with temperature control, pressure control, and so forth within the system, which is important when we're developing them for particular applications, including, for example, as illustrated in this schematic, irrigation. Next slide, please. Right. Also, the measurement and detection are important when we're dealing with these technologies. There are various techniques, light scattering techniques, tracking techniques which are available for doing it, each which have their characteristics, their benefits, but also their limitations. The only one in that list there, the resonance mass, is the only one that can distinguish effectively the bubbles, the nanobubbles, from nanoparticles, from solid particles. But we have other ways in which we can be sure that what we're dealing with in these applications are actually nanobubbles. Next slide, please. So why this is special? Well, it's really the stability and longevity that's relevant here, together with the fact that they can carry different gases and they can have different adherence upon the surface of the nanoballs, and also we can exploit the charge that is related to those bubbles. Next slide, please. I mentioned already that the nanoballs are believed to have these colloidal properties to do with the dispersal of the nanoballs within the medium and the propensity that they may have to aggregate or not aggregate, as the case may be. So that's an area of further research and development. Next slide, please. Surface charge, mentioned again, there are around these bubbles, and this was believed in the first instance to be an important factor in explaining the stability of these bubbles, that there are these ion formations around the bubble itself, which give rise to a layering of ions and a layering of charge outside the bubble surface. Classical physics would suggest that these bubbles would disappear in a matter of microseconds, but they don't, and they can exist under appropriate conditions for hours, days, even weeks, depending upon those conditions. And this area of stability research is a very significant one. There are a number of models that have been proposed for the stability of these bubbles. Perhaps more about those later. Next slide, please. So there are these chemical properties which are very significant in determining the size and distribution of these bubbles, including the alkalinity, the pH. The populations are favoured by more alkalinity, and this is reflected in this charge measurement that we can make called the zeta potential, and it can range in value depending upon the ionic content within the medium and of course the pH. Next slide, please. Gases are very important because the bubbles can contain different gases. We can use those for different application purposes. And they've been used in a range of applications, including removal of pesticide residues and pesticide alternatives, with oxygen, of course, root oxygenation and feeding, fertigation. Also now we're seeing process, because of what you can put on the bubble surface itself, the possibility of developing gene switching techniques. So you switch something on within the DNA, but you don't actually change the DNA. They're also being looked at for soil remediation. But in any of these applications, it's important that we understand the mechanism as well as the nature or properties of the bubbles themselves. The shell composition determines the stiffness, elasticity, gas exchange capabilities, and so forth of those bubbles. And also the response to applied fields. And we're looking at various applied fields, including electromagnetic fields, magnetic and electrical fields, and the effects that they have upon these characteristics. The choice of shell, of course, also determines the purpose and functionality. Next slide, please. So, right, surfactants. These are the agents which can affect the surface tension of a medium. These are significant in influence the size and distribution of nanobubble populations, and one can distinguish non-ionic surfactant and ionic ones as well, anionic and cationic surfactants and their various effects on the bubble population. And how they affect stability, because they certainly do affect the stability. So, next slide, please. Salts and various, the various salts can affect sodium chloride, for example, calcium salts, magnesium salts. They can all affect the size and distribution of the bulk nanobubble populations. The higher the valency, the greater effect in reducing the nanobubble size and distribution. So what is this, all this is pointing to? All these properties will indicate what we can do in the practical sense with regard to exploiting this knowledge, these properties of the bubbles themselves. Next slide, please. And of course, the content of water can be significant in this respect. There are many applications which produce media that are put into other media, such as for water treatment. But in the generation of nanobubble or bulk nanobubble media, an understanding of the water itself is clearly important. A lot of the preparations are using deionized water. But in looking at applications, clearly having an understanding of the nature of the water involved is clearly important. Next slide, please. Another very interesting feature to do with nanobubbles is the formation of free radicals, particularly oxygen reactive species. These are oxidants, and they can be used for killing off pathogens of various kinds. Almost agnostic in the sense that they can deal with viruses, bacteria, protozoa, and so forth, a range of pathogens. By introducing phages onto the surface of the bubbles, the prospect is also provided for pathogen-specific applications. So this is clearly an area of active research. And what is also important in this, although one can generate these bubbles by looking at microbubble collapse as a mechanism of doing this, in applications, it's important to know the concentration of these reactive species, and also in applications to consider the consequences of the breakdown products and how that may relate to the application you're dealing with, particularly in regard to pathogens, where ideally one's looking for a sustainable action of the media that is being used to kill the pathogens. Next slide, please. So there you have this range of properties which collectively form the basis for further study, research, and applications development. The technology itself is emerging. We're now seeing significant publications, number of the exponential rise in publications with regard to this technology, and also market reports. There has been one in a 2022 market report, and we're expecting to see more and more detail coming out of those project reports. But in all, it's indicating the importance of this as it's emerging technology. Next slide, please. One could generally characterize these emerging technology using these so-called S-curves. Given the appropriate data, one can actually determine the sigmoid fitting for these curves. This is just an indicative schematic to show the form of it and where perhaps we are on the life cycle with regard to nanobubbles. Because of the legacy issues that I mentioned for microbubbles, we're probably further up that S-curve in relation to where we may be with nanobubbles. Within the UK, we have an important foundation for developing the technology on a national basis. Within Birmingham University, there is this team led by Magrow and his team. It's a source of foundational research on bulk nanoboards, very important indeed. And also we have within the UK a substantive contribution to development of ISO standards for ultrafine balls, nanoballs, that is led by Dr. Steve Ward-Smith from Malvern Panalytical, who is also chair of ISO TC 281. And Steve will be talking about that just now.
Thank you for that, Anthony. So we've heard that this emerging technology that has its basis with microbubbles and that legacy tech, that we can't see the size of these bubbles, the size of a virus, and they can go from 10 nanometer to 1,000 nanometer. In doing so, Anthony just referred to the fact that our next presenter is Dr. Steve Ward-Smith, who is actually chair of the ISO TC 281 in fine bubble technology, who's going to go into some more detail for those companies and researchers that want to understand more about what is available out there and what certifications required. Over to you.
Thank you. Okay, yes. So thank you for having me today. As Les just said, I'm Dr. Steve Ward-Smith from Malvern Panalytical. I'm also the chair of ISO TC 281, as was said previously, and also the kind of chair of the UK Mirror Committee for this, which is LBI 50. Could I have the next slide, please? Okay, so to start with, I do a lot of standardization, as well as TC 281. I'm also on another ISO committee. So really, what is a standard? Well, a standard is really a method or a set of rules which goes into a document that can be used to guarantee certain performance if followed. It can be used by you to, as part of a method, by doing things this way, you should get results. Or it can be used if you buy a piece of equipment to use you as kind of guarantee your consumer rights. If it follows this standard, it should actually work. So it does give you some degree of protection with buying, say, buying a bubble generator. If it follows the standard, you'd expect it to work. If you bought another piece of equipment that should generate bubbles and it met a standard, yes, you'd also expect it to work. So it's useful for vendors who can provide expectations to customers that they've made it in a correct way that will guarantee results. And then customers who want to buy something to meet a need, or researchers who want to follow a method to follow activities in a certain way. Next slide, please. Right. So as I said previously, I'm the chair of ISO TC281. If you want to find out a little bit more about us, if you follow the link in the slide here later on, that will take you to the kind of committee homepage. And the what we have here is we are 9 years old as a committee. We have written 18 standards so far. We have 10 more standards in the works in some degree of completion, and many more kind of like in the pipeline as such. We currently have 3 working groups within TC281. One is on terms and definitions. The second working group is on methodologies for measurements and characterization of fine and ultrafine bubbles. And the third one is on applications. We have many different countries around the world which are members, which are such Australia, China, Germany, Indonesia, Japan, South Korea, Russia, Singapore, UK, and the USA, with a fair amount of countries as observers. The Secretariat, so the kind of like the country that does a lot of the back-end organization about submitting standards to ISO, organizing votes as such, is Japan at the moment, and it has been since the start, because Japan was kind of instrumental in launching TC281. But both of the chairs, of which I am the second, of TC281 so far have both been British. Next slide, please. Right, so what we're about, this is our kind of scope. So what if you go to our webpage, it says what ISO TC281 is about. It's about standardization in fine bubble technology, covering the terminology, characterization and applications of fine bubbles of gas, generally in liquids, and generally were less than 100 microns. So we cover small microbubbles and then ultrafine bubbles. Okay, next slide, please. So we said the 3 working groups are terminology, characterization, and applications. Okay, next slide, please. There's 4 terminology standards so far. And in the main sample preparation section, we also have standards on sample prep, storage and transport and extraction of bubbles into vessels for transporting them around. We have a measurement technique matrix, which goes through the core technologies and their fundamentals and how you might want to use them. More detailed guidance on microbubble characterization and elimination methods. Elimination methods, it's probably worth me pausing, talking about that for a second. When you generate bubbles, you're not always just generating bubbles. Sometimes you may get some contamination from the bubble generator or the liquids you've got in there. If you're generating bubbles in the middle of a lake, you may get bits of soil or dirt and things kind of in there as well. So how do you know you're generating bubbles if you measure them? Because there could be bubbles and particles present. So the elimination methods is if you count the number of particles or measure the number of particles before you eliminate the bubbles and after, the difference in population must be down to bubbles. So if there's a change in what you're actually measuring before and after elimination, therefore you know it's down to bubbles. And you can eliminate by using ultracentrifugation, ultrasound, but probably the most kind of effective way is freezing. So you generate your bubbles, take the sample, stick it in a single domestic freezer, turn it into an ice cube for a little while, defrost it after a day or so, remeasure it, and then the difference in population is down to your bubbles, because the bubbles don't survive freezing. So and then the application standards. So far, we've got standards on water treatment, several standards on cleaning in multiple arenas, lettuce growth through hydroponics, and quite a lot of standards on seed germination. So why do we want to standardize in the first place? Well, it allows different countries to speak the same language, do things the same way, allowing scientific comparison, and then enable, if you are shopping for a bubble generator, to be able to try different manufacturers on, and then pick which technology is the most appropriate for your needs. Next slide, please. Right, so in terms of like the big application areas we've done so far, cleaning, the standards on cleaning machine oil on metal parts, salt on bridges. The Japanese a local government has spent a lot of money on bridge cleaning equipment when they have salt in winter, like we have in the UK. The salt solution gets onto bridges and generally corrodes them, and they use fine bubbles in the washing of a local government there to clean the bridges. And they also use it in service station toilets for the same effect as well, without using detergents. There's also a standard on floor cleaning, and then there's projects in the way on cleaning textiles and shower heads. And there's also a lot of interesting products, especially in China and Japan, of which we see one on the next slide. Next slide, please. Okay, we have the Toshiba Zaboon here. This is actually an ultrafine bubble washing machine. It's now in its second generation. It uses a fine bubble generator with a pressure tank kind of in there. It mixes air with tap water and then pressurizes and creates micro bubbles and ultrafine bubbles. The ultrafine bubbles kind of get between the fibers on your material. They deliver the cleaning ingredients to the dirt, but they also allow extremely low temperature washing machines. So this is beyond what we see even in the UK with the kind of environmentally friendly washing machines, because we have some micro bubble ones available in the UK, but we don't have this technology available in the UK yet. But it does allow very low temperature washing. Next slide, please. Okay, agriculture is a huge part of TC281. There's been 4 standards. So, can you go back a slide, please? Up and forward. 1 and forward 1, please. There we go. That's fine. Thank you. So agriculture is a huge part of what we got. There's also an upcoming ISO, task group, which will probably birth a new ISO working group, of which fine bubble technology will be a small part on precision agriculture. So I know that will be of interest to some of you today. So that will be a separate ISO committee that's kind of coming. There's been a lot of published data so far on the use of fine bubble technology in growing ginger, lettuce, and fish farming. UFB has been used to produce calories in mayonnaise by using it as an artificial oil as such. So it gives the same creamy texture, but no calories because it's air and not oil. Carbon dioxide bubbles are used for transporting fish to sushi restaurants, because if there's lots of carbon dioxide present in the water, the fish get sleepy. So you essentially put the fish to sleep in water tanks. They're not stressed, and they're transported to the sushi restaurant where they can be served up, but they don't die in transit or aren't stressed and injured. So you can deliver prime fish to the sushi restaurant by kind of like just putting the fish to sleep during transportation. There's also been several Japanese government-sponsored agricultural trials for use of fine bubble technology across Southeast Asia with great success in Singapore and Thailand. And there's been a lot of work done on cleaning as well. Cleaning vegetables and salad washing has been quite a lot of application areas as well. Next slide, please. So I'm part of the UK Mirror Committee as well. There's representatives of agricultural companies, universities, and bubble generator companies as part of that. We have the honor of hosting the next ISO meeting on the 31st of October to the 2nd of November. And we're also open to new members. So if any of you fancy working within standardization, we'd love to have you. Next slide, please. So where do we at Malvern Panalytical fit in? Because I'm not an agricultural guy, even though I did have my PhD in a food science department in an agricultural part of Nottingham University. I'm interested in the characterization end. There's several different technologies you can actually use for characterizing fine bubbles. Dynamic light scattering, laser diffraction, as Tony pointed out, you can measure the charge on the particles, the zeta potential, because they've got a great charge on them, which makes them very stable. There's others, particle counting, ultrasound, static multiple light scattering, and image analysis, which are mainly sizing techniques apart from zeta potential. But the technique with the most installs within the technology is the one I've got at the top, which I'll just mention now for the first time, which is why I left it to last, because it is the most popular technique. Tony had this in some of his slides, is a technique called nanoparticle tracking analysis, NTA or PTA for short, which we develop. Next slide, please. So the principle of measurement here, it's a bit like dynamic light scattering as you measure Brownian motion. So the particles are bombarded by water molecules, they move around. Small particles move faster than large particles, and you can work out their diffusion coefficient and use the Stokes-Einstein equation to work out their size from the diffusion coefficient. Next slide, please. Nanoparticle tracking analysis is the gathering of information and comes from assessing individual particles rather than averaging over a bulk sample. And that's the difference between it and dynamic light scattering, which is an ensemble technique and measures everything. Nanoparticle tracking analysis tracks individual particles one by one. Next slide, please. So what we've got here is here we had a bubble generation experiment I did at Malvern Panalytical a couple of years back. We took water with a supplied bubble generator, and we measured the sample at a variety of different time points. To start with, we were getting at the order of 10 to the 7 particles per mil, and then over about 3 hours or so, we got up to into the order of 10 to the 9. A lot of people think bubble generation is a fairly instant technology. No, it often takes, if you've got a recirculating generator, it can take several hours to get up to 10 to the 9 or so. And some of the applications are concentration dependent. And that's why NTA is popular, because as well as size, it gives you concentration. So we're able to measure the concentration because really you need a minimum concentration for viability for a lot of the actual experiments. Generally, for a lot of applications, you need to be of the order of 10 to the 8. But if you can be higher, like 10 to the 9 is even better. Next slide, please. And here we have, and Tony alluded to the long lifetime of ultrafine bubbles, the same sample 3 months on. So, and it still had 3 times 10 to the 8 left in it. And I think we even came back to this about a year later, and we still had detectable amounts of bubbles in this liquid. But we did leave it in the fridge. So if it does, they do keep very, very well ultrafine bubble water if you stick it in the fridge. Out of the fridge is not quite so good, but it gives an extremely long lifetime in the fridge. Next slide, please. Okay, and now that's really the end of me, but obviously it has a very, very bright future. We're going to be, especially on the applications end, which brings us on to our next speaker. We'll be talking about a lot how the growth in applications in this particular area.
Thank you for that, Steve. And thanks for pointing out the importance of standardization globally and the existing uses across cleaning, transport, and particularly coming back to the Agricultural Centre, where we know Innovate have put quite a lot of funding in recent years. A quick reminder to everybody that's listening in that if you have questions, you've had 1 or 2 already put in the chat, if you could please put your questions there, and Richard Glass will pick those up for the panel towards the end of the session. I'm now going to switch back to Anthony Finesse, who's going to cover off the environmental significance of bulk nanobubbles for precision farming, especially meeting global challenges.
Environmental significance of these bulk nanobubbles for precision farming, as indicated right at the very beginning. when we're looking at practical applications, there is this commercial objectivity. But if we can combine that objectivity with solving global problems, so much the better. So the slides that follow are really to draw our attention to the issues that we have with environmental matters, and how perhaps the nanobubble technology can assist in solving or part solving some of those problems. So next slide, please. Right, now this is a schematic which shows the various planetary boundaries that contribute to the status with regard to our environment and the various factors which affect them. Some of them are at dangerous levels, indicated by the orange sections on that schematic there. This arises from a group in Stockholm Resilience Centre that did analysis based on earlier analysis of environmental dimensions. Two aspects of this just require a bit further definition. The biosphere integrity, that's also known as loss of biodiversity, recognizing the interdependencies of species and focusing on the impact of humans and on ecosystem functioning. And the EMSY, that's the extinctions per million of species years. So as an indicator of that degradation in biodiversity. And novel entities, these are relating to toxic and long-lived substances that humans release into the environment, including heavy metals, industrial chemicals, organic compounds in particular, and also pesticides. So next slide, please. So what I'd like to do here is to, next slide, please, is look at these various dimensions, the various planetary boundaries and the potential significance of nanobubble technology in tackling some of those problems. The novel entities, because we have oxygen reactive species or bubbles that contain oxidative agents, one can explore the possibility of removing or oxidizing some of these novel entities, or removing them by some flotation techniques. Flotation techniques have been used extensively in the past with respect to microbubble technologies, and now being used more and more as well in applications involving the more stable, the longer living nanobubbles. So, for removal of pesticide residues, for example, that's a possible use for the bulk nanobubble reactive species bubbles. But also the prospects of developing water treatment processes, products and services related to tackling these novel entities. Next slide, please. Biogeochemical flow is very important from the farming standpoint, because these involve particularly nitrogen and phosphates, which are at dangerous levels already with regard to that planetary boundary, and we need to reduce the amount of nitrogen that's going into water systems, for example. There are techniques that one can use, again, exploiting flotation methods for removing nitrates and phosphates, with possible fertilizer recycling potential as well. The cost of fertilizer going up considerably if we can do more to recycle those fertilizers, or reduce the dependency through more efficient processes, precision processes within farming, so much better. And some of those processes can involve this bulk nanobubble technologies. So, prospects for developing water treatment processes, products and services. Next slide, please. Climate change, well, this is brought to our attention very forcibly over the last day or so. increasingly significant as a planetary boundary, and we're drawn more and more to anything that can help in reducing the amount of emissions which contribute to climate change, the release of the greenhouse gases into the atmosphere. And that raises potential too for applying nanobubble technology in areas where, for example, one can deal with bacterial release of ammonia and subsequently nitrous oxide, which are contributory to these emissions and the greenhouse effects. So oxidative nanobubble technology, exploiting reactive oxygen species and other oxidants, seen as a platform for tackling this pollution problem. In a modest sort of way, but it's part of the actual armoury that's available to us in dealing with these emissions. Treatment of soil bacteria that produce ammonia and nitrous oxides, as indicated. Possibly with phase development, where we've got targeted pathogen treatment within soils. So good prospects here for developing water treatment process, products and services again. Next slide, please. Water usage. Increasingly, we're seeing a need to look after our water. And all these are linked, these planetary boundaries are linked in various ways. Climate change with regard to water usage, for example. And this is the boundary which is concerned with freshwater usage. Concerns arising in terms of access to water and water usage. And part of that concern is to do with pollution as well, and water pollution involving organic compounds, novel entities, materials, calling for enhanced water treatment methods. And as with climate change, there is increasing incidence of river pollution, ecosystem damage due to raw sewage discharges and so forth. Again, oxidative properties, not just reactive species, but other oxidants that one could put into these bubbles, or other environmentally friendly oxidative agents that one can use along with nanobubbles that are also environmentally friendly in terms of the products, the reaction products that come from those applications. So, prospect for bulk nanobubble extraction methods are seen as platform for tackling these pollution problems involving both organic and inorganic components, and potentially exploiting also particles, microplastics, dealing with microplastics, for example, or using micro particles as well as the bubbles themselves in producing treatment solutions. So prospects for developing water treatment processes, products and services. Next slide, please. Right, there's also land usage, available land usage, clearly a significant bearing upon food security, climate, carbon sinks and biodiversity, linked in with the needs to secure and protect and manage the soil resources and repurpose land according to food and environmental needs. So soil redemption and management and their management constitute an important aspect of the strategies for land change and usage. And as far as the bubble technology is concerned, oxygen carrying and oxidative properties of bubbles can be used to enhance food production methods through nutrient and oxygen delivery to plant root systems, seed germination, soil conditioning, and so forth. So it's a sort of indirect way in which the bubble technology can assist in dealing with this particular planetary boundary. So again, prospects for developing water treatment processes, products and services. Next slide, please. Biosphere integrity, with a particular aspect of this, of course, is to do with the influence of pesticides on the biodiversity. So if we can find ways in which we can reduce pesticide usage, we can remove pesticide residues and so forth, that will contribute to the securing our biodiversity. So again, oxygen carrying oxidative technology can be used for more environmentally friendly removal of pesticides, insecticide residues, and development of potentially of bulk nanobubble based alternatives. There's again prospects of developing treatment products and services. Next slide, please. Along with all these planetary boundaries, we also have the economic issues that relate to the sustainable development goals that have been with us for some time now. And as a change management tool linked intimately to donut economy or circular economic frameworks are now being considered important in tackling these sustainability issues. And again, one can see prospects for applying bubble technology, potentially along with other technologies as well, for offering solutions with regard to these sustainability goals. Next slide. And these, of course, are the sustainability goals that we're having to tackle. Some are more obvious with regard to potential applying the nanobubble technology than others. But by and large, one can think in terms of the sustainability goals. What, knowing the properties of the nanobubble technology, could they be applied in dealing with that particular sustainability development? Next slide, please. I mentioned already the move towards more circular economic models, and certainly the UK government is moving in that direction. There is one model which I think offers even more insight and a platform for looking at potential solutions that links the social foundation to the ecological ceiling, and that's this so-called donut economic model. And as you can see there, you've got the social one, which in many ways covers a lot of those sustainability goals that we've seen just now, but includes things like energy and food and so forth. So very significant in linking those with the planetary boundaries as well. So for many of these sector problems, nanobubbles can be seen to have potential in easing or solving these problems, many based upon exploiting legacy applications that we've seen earlier, notably involving the environmentally friendly oxygen active species, flotation removal methods, and nanobubble carrier capabilities for gases, nutrients, for example, in fertigation, and target agents, gene signaling, as I mentioned, as a future prospect in this respect. Next slide, please. Right, so health being one of those sectors of social foundation. We saw that the COVID-19 pandemic initiated a significant increase in demands for disinfectants and cleansing agents, wherein opportunities were recognised for bulk nanobubble technology as well, containing oxygen reactive species and also oxygen such as ozone gas. These are developments that can extend to food treatments and to implications for complementary non-vaccine early stage treatments in medicine as well, but of course requiring appropriate controls on the research and development and application of such technologies. But there are these prospects for developing bulk nanobubble treatment media and media delivery products for primary food and disinfection, for example, for which there are now some established markets for those technologies. Next slide, please. So food, we've also made a lot of reference to food and food security. Opportunities here seen for replacing chlorine-based treatment of vegetables and meat were recognised for these nanobubbles, using oxygen reactive species and ozone gas, for example. Greater opportunities seen for exploiting other nanobubble properties for influencing plant-based food production, efficiency, yields from seed germination to harvest. An interesting aspect with regard to seed germination, for which are now emerging ISO standards, is that in using oxygen, for example, to a higher population of bubbles can result in a detrimental effect on germination. Getting the right level, the population level, is beneficial and can be beneficial with regard to seed germination, and also depend upon the type of seeds that one is dealing with. Well, this just points to the very important aspect of understanding the nature of the application you're going to be dealing with, and getting an understanding of the mechanisms involved in the applications concerned, the process of seed germination and so forth. There are also prospects here for reducing needs for pesticides and insecticides related to food production, including the potential for nanobubble-based alternatives. Prospects again for developing treatments, media delivery products for primary food and disinfection. Also foundational research opportunities related to mechanisms and in relation to plant production. And again, there are established markets for cleansing products. Next slide, please. Water, again, this comes up, particularly with regard to the Solitary Foundation, and it's seen as a planetary body of rising concern over water pollution, as I mentioned, and what goes into the water systems. And with climate change, there are increasing incidents of river pollution, ecosystem damage, and so forth. So again, prospects for developing nanobubble treatments, media delivery products, and so on. And again, established markets. Next slide, please. Right, at the farming level and with regard to environmental and soil, one can see all sorts of prospects for applying not only the nanobubble technology, but for example, magnetic assist spraying technology. At the leaf level, with regard to foliar feeding, fertigation, gene switching, abiotic elicitation, and then in the soil level, soil redemption, seed germination, root oxygenation and feeding, pathogen treatments, dealing with ammonia and nitrous oxide emission control and so on. So there are principal areas now emerging from research and mechanisms for agricultural applications. Next slide. And we can be exploiting too in this process those microbubble legacy applications we see for water treatment and pollutant removal, mineral flotation techniques, bioremediation of groundwater, industrial wastewater treatment, disease and pest controls, and acceleration of metabolic functions in plants and animals. Next slide, please. Right, so where are we on this this S-curve? We're probably in these early stages already, but it's important that in looking at this technological development and where we are on this, that we recognise the importance, the need for mechanistic research to put things on a more practical level with regard to applications, much firmer foundation scientifically for that application. Recognising the need for applied research systems research to put generator developments on a firmer foundation, development of ISO standards and performance factors, translating knowledge into commercial objectivity, and investment to meet global solutions for food security, sustainability, and environmental needs. Next slide, please. So how do we get started with this technology? Well, two aspects to this. Where necessary, gaining greater awareness through perhaps demonstrations, establishing an interest group on nanobubble technology. That's, I think, really quite significant. ISO standards development, publications and technology bulletins, liaison with Agri-EPI centres, lobbying of government for governmental intervention. This has worked in the past. I've had experience of this with radio frequency technology, where we did get government support to set up an investigative study, a very successful investigative study in the application of that technology. So it's not out of the question that one could get such support for nanobubble interventions. Product suppliers, support information from them, training events, technology and application providers, a growing number of these, of which Liberty Produce, and Alex will say a bit more on that in the next presentation. These can be very important because they have the platforms for getting these applications into the field. Then there's practical experience through small-scale investigative studies, retrofit trials linked to irrigation, spray delivery processes, for example, system trials for horticulture, vertical farming, for example, system trials for agriculture. The list goes on, but these are some examples of where we can get started. And it's important that we start a forum to discuss and develop this technology because it is at such an early stage. This is critically important if UK is going to establish some sort of lead in this respect. Thank you.
Thank you for that, Anthony. Clearly, you've identified how nanobubbles can help tackle some of the planetary boundaries and the issues around them going forward, especially with your water uses, chemical, replacing chlorine-based treatments and seed germination, to mention but a few. Now going to move over to and introduce Alex Giles, who was the co-founder of ICNI Labs, an innovation accelerator, specializing in mission critical science. And in particular, they trial some of Liberty Produce, an ag-tech R&D business with their headquarters in Dundee at the James Hutton Institute, where Alex is a commercial director. So Alex, if I can pass on to you, please.
Thank you, Les, that's very kind. I must say I'm quite trepidatious to be the last speaker after following so many experts. So I'm certainly going to keep this very, very brief. As Les mentioned, Liberty Produce, which I'm one of the directors of, is an ag tech business specialising in R&D in the vertical farming environment. We're particularly interested in the connection between vertical farms and advanced greenhouses, a hybrid approach. I'm firmly of the opinion that we need to be developing technologies that have applicability in both those sectors. And we have at Liberty done that in things such as lighting, and we are now developing on Innovate UK funding a nanobubble technology. Next slide, please. Thank you. And as I said, my esteemed other panelists have gone into this in far better detail than I would ever do. So I will just leave it to say that nanobubbles as a technology are clearly becoming recently of great interest. There's a lot of research going into it around the world, which we are just a small part. Where we came from this is to look first of all where we were first aware of it as a technology is in its large scale applications in the wastewater treatment environment. And essentially what our Innovate funding was designed to do was to take those very large scale systems and ask the question whether that could be scaled down into a system that could be installed into a vertical farm, or for that matter, into an advanced greenhouse system. And I'm pleased to say that our research has allowed us to do that, and we do have a system installed up at the James Hutton Institute, which, as Les mentioned, is where we are headquartered up in Dundee. I'm more than happy after this call for people that are interested in collaborating with us to have a conversation about people coming and seeing what we're doing up there. Next slide, please. So as I mentioned, I'm going to jump straight past this because people have spoken about this at great length. We have concentrated very much on the improvements in yield that we think that vertical farming can do. Like a lot of, in common with a lot of our vertical farming technology partners, we started in a world in which we were developing leafy greens. That's pretty much, I think, where everyone starts in the vertical farming world. But we've moved out from that into some quite more, should we say, interesting crops, what a better term. And under a Eureka project, combined funding with Singapore government and the UK government, we're actually in the process of some work in Singapore on Asian greens as well, where again we think that the nanobubble technology can have some real applicability. Next slide, please. So I'll just say, and these really I only do have a couple of slides, that the exploitation potential that we see as the number one thing to look at, which we are very keen to talk about partnerships, is in the micro nutrition uplift. We think that we can see substantial improvements. We think that that can go into some tailored crops. And from a straight commercial point of view, which is where I sit in this, we think that this is the type of things that gives you access to some of those really lucrative markets. And I would just say as a sideline that one of the challenges of vertical farming in general is where we've all started is that often vertical farms are being designed and are growing actually quite low value crops, and that makes it very challenging economically to make that commercially viable. So if you can start taking this technology to allow you to access some of these what we see much more lucrative markets, these superfood premium markets, the baby food market, the lifestyle markets, for want of a better term, we think you can clearly add substantial profit and make your vertical farm in general be a much more commercially viable and valuable product. Next slide, please. Just the next slide, please. Thank you. Thank you. So, what we're seeing, we're thinking that these bubbles can act essentially as a nutrient transporter. That clearly has a great uplift in the types of crops that we would want to grow. We can improve the crop nutrition. We can reduce the nutrient requirement that we're putting in. Again, you can see how we're essentially improving the OPEX of our capability. And this can either be done as an end of growth cycle loading. It's actually very similar to the types of R&D that we've done around lighting systems, where we've talked about how lighting formulas at the end of the growth cycle could increase nutrient. So actually we see this very much as part of a combined project as well, both the lighting and a nanobubble system. Or you can use it as a daily dosing system. May I slide? Well, there you go, that says it all. Thank you. As I said I would be brief, knowing that my fellow panelists are much more expert than I am. But as I say, I'm happy to answer questions, perhaps more usefully for people, if people would like to drop us a line and talk about coming and seeing us in Dundee and seeing what we're doing. We'd be delighted to host you. Thank you very much.
Thank you, Alex. That's very much appreciated, pointing out the opportunities that Liberty Produce have identified. I'm now, if I can, going to ask Richard Glass, who's works with CHAP at Soil Health and Protection, has done for as Innovation Sector Lead, following 20 years with the Food and Environmental Research Agency, where he's had exposure modelling and development of novel control techniques such as biocontrol. He worked in Colombia with projects looking at spray deposition in coffee, and Southern Europe evaluating new active substances and operator and worker safety. Richard, you've been on a couple of projects recently sponsored funded by Innovate into nanobubbles. So you're in a great position to manage any questions that have come in. So I'll hand over to you, Richard.
Thank you very much, Les. So yeah, if anybody has any questions, if they put them into the chat, we have a few through already. And the first one is for Steve. Somebody's asking, how do I get involved in standardization?
Well, if you're an expert, really just email me or let me know, and I can get you signed up through BSI as an expert onto the committee. And now is a good time because we are hosting in the end of October, beginning of November. So your first meeting, which you still be in time to get involved with, would actually be on home turf in London.
Very good. And another one to you, Steve. What wavelength laser do you recommend for NTA?
Generally as low as you can get, really either a blue laser or a violet laser, really. The red lasers, which are some of the machines may come with, they're a little bit big. They'll be fine for microbubbles, but they're the very small end of a nanobubble distribution. They're not going to have great resolution there. So really you want a blue or a violet laser.
Thanks, Steve. And now there's some questions for Tony and Alex. Maybe first of all, Tony, being asked about what is this disruptive technology and what commercial uses are there for nanobubbles?
Well, I tried to cover those points in the actual presentation. Clearly, time is against us. Disruptive technologies, as indicated earlier, these are technologies which are relevant to a number of industrial sectors, not just to one. So relevant to industrial sectors and commerce, but also can influence radically the performance of processes, for example, tens of percent improvement as opposed to 1 or 2% improvement in process, but also can contribute to developments of products and services in a radical and revolutionary way. There are technologies that also provide these platforms for innovation in various ways. So hopefully that covers that point. As far as commercial uses of nanobubble technologies, they follow on from the legacy that I mentioned with regard to microbubbles, and certainly you've got very significant developments with regard to water treatment, including removal of pollutants from water, large-scale applications that involve water treatment of various kinds. And there's one company in particular, is potentially one of the leaders with regard to nanobubble generate technology, Molia, and with respect to water treatment and looking at applications. They've had significant seed funding now for looking at applications in agriculture, but they've got a lot of experience with regard to treating water systems, large systems, river systems, lake systems, golf course water systems, and so forth. So that's a significant area. There's another significant area in industry to do with flotation, mineral extraction, where nanobubble technology is taking over from microbubble technology. Disinfectant, clearly that's an area which has emerged quite considerably since the COVID pandemic. But now what we're seeing is further applications that exploit those carrier capabilities, both for gases within the bubbles themselves and for adherence to bubbles or in association with bubbles.
Thank you, Tony. Alex, anything to add about commercial uses of nanobubbles and companies exploiting the use?
No, I mean, just to say that I think over the next year or so, we're going to see an explosion in all the different applications. Steve mentioned some fascinating applications that I was not aware of. So I think it's one of those technologies that has people who are doing science behind it, understand it more and more, we're seeing just an absolute explosion in applications. Clearly, not just ag-tech, but plenty of ways, forward. And certainly, I would expect within the next year or so that there will be companies talking about entirely brand new ideas that we haven't even thought about now.
And question about are there different ways of producing generating nanobubbles? What are the most plausible methods? Tony or Alex?
Steve, do you want to take that one?
Yeah, I mean, I can do that. I mean, there's all sorts of generators which come in lots of different shapes and sizes. And sizes being an optimum part, because some of these generators are the same size as a washing machine and can have an extremely large tank. And I've got one that's quite effective, which I keep in a desk drawer, which is about the same size as a pen. So they can. So there's lots and lots of different technology. I mean, generally you'll need some sort of air, and some are generated by kind of pumps. Some could even be generated by ultrasound. There's ultrasound as well as killing bubbles can also generate them. But there's some are also kind of like generated by things like this carbon fiber, which is almost like a fish scale, which can kind of like separate out and things can permeate through them and generate bubbles, and that works quite well. So
yeah, in the presentation slides, I have put a short list of generator methods in there, including reference to the nucleation mechanisms that are involved in those generator products. But clearly there are ones which are based upon the use of Venturis, for example, with gas inclusion, membrane exchange. Mixer technology is another one, which is using blender type shear mechanism for generating bubbles and so on. And there are a number of companies now producing generator products. What is important, of course, in this is knowing how to scale for particular applications. In some cases, one is going to require considerable volumes of this medium, and you've got to have the generator capability to do that. Yeah. So if you want to look at applications, you've got to look at the size of the application and what the implications are for the nanobubble populations required in those applications.
Thank you. We have a question from Benjamin Langendorf. Who would be the best contact to speak about applications in agriculture, such as plant protection?
Well, if I can take that, I think actually, if you can, we'll pick that up, Benjamin, and circulate that with our colleagues. And if we get a bit more detail as to what you want to try and resolve, then part of Agri-EPI Centre's remit is to help source and enable an answer for that. So we have the phrase "together we can." So we'll pick that up and come back to you.
I just had a point on that part of the feasibility study that we had with this innovation funding was to look at the issues of plant protection. Yeah, and with regard to the pests that one has, and the conditions that arise with regard to plants and how you can protect them. And one can see potential with regard to nanobubble technology, particularly oxidative bubble technology that can deal with a range of pathogens and a range of conditions, mold conditions, for example. As I indicated very early on, there's this sort of agnostic properties associated with these oxidative agents and these bubbles, that they can deal with viruses, bacteria, protozoa, fungi, molds, and so forth. Yeah, so it's a question of looking now at where one can exploit various platforms in relation to particular plant protection problems.
Yes, it's something that we've discussed, isn't it, Tony? Whether there's a potential plant protection property using nanobubbles, and certainly with CHAP and Agri-EPI, certainly be putting together proposals to follow on from the project that we've just finished to look to develop more uses in agriculture.
I mean, a very significant property associated with bulbs in that respect is their penetrative capability, because they're so small. They can penetrate into leaf structures and indeed to insect and other pathogen structures.
Yep, very good. That's the end of the questions that we have, Les. So if there's no more questions, I'll hand back to you.
Okay, well, if I can then just summarise, clearly, as Alex, Steve, and Anthony have all referred to, is that we're just at the beginning of learning about nanobubbles and where we can go with them, and they do have potential remarkable qualities which we need to work together in order to understand more fully and utilise them for the benefit of agriculture and the other wider sectors where possible. So if you have ideas and suggestions or want to work with us as part of a consortium or collaboration, then please contact myself or any of my colleagues on today's webinar, and we'll be pleased to work with you to see how far we can go with the project. So thank everybody for your time. Thank you to Anthony, Steve, Alex and Richard, and the backroom staff here at Agri-EPI Centre, and look forward to seeing you again on another webinar. Thank you.
Thank you.